We're on. So, some of you had told me that the lectures have been going a little too fast, and that they would like me to use the blackboard, but as we discussed, I think, the very first day, I can't use the blackboard in this room because unfortunately, this room is such that you guys can't see, right? And so, of course, I have my iPad and I can write real time. And I think just it sort of got to me when we decided I can't use the chalkboard, and that's how I usually use the chalkboard. And also having to stay stationary the whole class time, of course, you understand. So I kind of had to use the last few class times just to get used to this, but I'm going to do more real-time, writing for the lectures. And also because we went over a very important topic of evaluating forces on submerged objects. I decided to start off by, okay, this is the one that I posted. Okay, I decided to go over, start off by going over an example problem. And so, okay, so today, so let me just copy page and paste. Okay, so, all right. That seems really light, but you can see all that? I think it's just this page, right? Because it's brown background. Okay, so today, so this is maybe next time we'll start. And so I just thought of this. Otherwise, I would have put this in the lecture, but let's go over, gosh, let's see, how about forces on submerged surface example. Okay, so we'll just work out an example to make sure everybody understands how I'd like things to be done. And then the last two topics are fairly quick because they're not really the main topics, but I do have a homework assignment on buoyancy, a homework assignment on rigid body motion for you to get a little more familiar with these. But since this is such an important topic, I'm going to go over an example. Okay. So let's see. So now let me. Okay. Need something here to. Now what happened? Oh. Oh, shoot. I was going to redo everything, and there it goes. Chalk is so much more robust. Well. Okay. All right. So we went over this last time, and remember, if we assume that so we have a liquid and a free surface, and then there's atmospheric, air, and we have some surface that is submerged in this liquid, And for the case of constant density, the pressure variation, so this is pressure with depth, can be expressed in this way, our basic hydrostatic pressure variation, in terms of depth, coordinate positive going down, and assuming density is constant, starting off with H equals 0, P equal P naught, the pressure at the free surface, and it's a linear increase with depth. And so this linear increase, okay, so at this depth, okay, is this pressure, right? And here we just increase in depth, okay, and then the pressure increases linearly, and so will the corresponding force. So rather than a single force or a uniform force, if it were a constant pressure, we have this distributed force increasing linearly as we go downwards, right? And so we want to, and we can think of, rather than this distributed force, replace the distributed force with a resultant force. And so this differential force we know to be minus PdA, and then taking the differential force and integrating over the entire area is going to give us this resultant force. And we can change this to a equation for just the magnitude, since the magnitude, am I still on? I think so. Because the direction is by inspection. We know the force due to the pressure is always towards the surface, okay? And so we went over that, and I summarized here to determine this resultant force. The direction is by inspection. The magnitude, so we can change that equation to the magnitude and just take the integral of pressure over the area. Okay, and the pressure, if density is constant, we know that we can use this with h being the coordinate depth. And then along with direction and magnitude, we need to determine the point of application. And so we equate moments. So the moment of the distributed force would have to have, or be the same, cause the same moment as the moment of the resultant force. And so actually, more generally, I could write this as R cross F. Okay, and then this would then be R cross dF over the area. So this is, or this will work out to be the area, when you, again, replace the, when you then replace the dF with PdA. So, okay, and then this is the moment arm. Okay, so let me just now work out an example. So I quickly put this in there, and this happens to be the last year's midterm 1 problem, and so but it's, I think, it's very instructive. So we'll go over it. Okay. So, a submerged chamber, okay, so we have this chamber that is submerged in water. So here's our free surface, an atmospheric pressure existing above, and we have water, okay, and so this hatch, this chamber, okay, is submerged, and it contains air, okay, and the air is at some uniform pressure P sub I. So remember, unless we have a large change in elevation, a gas, we can basically neglect the pressure change with elevation or depth. as compared with a liquid. Okay. Now this chamber containing air is equipped with a hatch. So this is the hatch, and it's hinged at point A. And if this pressure, which will act uniformly over the hatch, so we'll have a resultant force on this side, okay? And if the pressure is sufficiently high, okay, then this hatch will open. So this force due to the pressure of the air inside will cause a moment about A and open and overcome that pressure due to the liquid, which will cause a distributed force on this side. Okay? The hatch is rectangular, so it has a length L, okay, and a width W into the page. And it also has a mass M. Okay, so it's kind of a heavy hatch, all right, with mass M. The hatch is hinged with friction at without friction at point A. And point A is located at a depth D below the water surface. Okay? The density of water, rho, is a constant, and we determine P sub I in terms of the known quantities. So we want to determine P sub I, just the value above which the hatch will open. Okay? So does everybody understand the physical problem? Okay? And basically, you're going to want to sum moments. And the hinge is the convenient location to sum moments. Okay? Now, let's just go through step by step. So we first have one of the assumptions. So I indicated the known, and then what we need to determine. And, of course, we have the sketch here of the physical domain or setup, but we'll need to add to that or draw some other sketches, perhaps. One basic assumption that we want to indicate is that rho is a constant. Okay? And so, okay, basic equations. So we have, for our basic equations, these equations here, for example, we have our force, resultant force is the integral of PdA over this area. We can also, since we assume density is constant, we can use this hydrostatic pressure equation. And then, either this one or this one, some moments. Okay, so let's write these down. Okay, and whether or not you end up using these, and we can write it in vector form or scalar. At least, you can start thinking, okay, this is a submerged surface. We need to determine force and moments. And so you can lay out some basic equations that may be applicable. We have the pressure variation P is equal to P naught plus rho GH. And so you have to fully understand how this pressure, the equation works. And you do so because you went over the integration of that, right? And so right away, we can define our H coordinate. Remember, a sketch of the physical configuration, and then coordinate system essential. Coordinate system essential. And then summing moments. So we can write, we can take this equation here, either of these equations. So on an exam, I would have an equation sheet with the vector form of this and then this. So we can write, R cross F sub R is equal to the integral of R prime cross dFR. Okay, now the analysis. Okay, so if you're not sure how to go about this, okay, you can sort of follow the basic procedure. So first we determine the direction, perpendicular to the surface towards the surface, and then the magnitude of the resultant obtained in this way, and then the point of application y sub r obtained in this way. Okay, where this essentially is this written in scalar form. So a few things, first of all, because it's inclined, and the surface begins at a depth d. And so what we might, and we also have to consider the weight of this hatch along with the air pressure and the force associated with it on the other side. So there's forces involved. So it's a good idea to draw a free body diagram. So let's just, maybe, so we have our surface, and so we're going to have the distributed force on the top side, so we can indicate it as this, okay, or you can indicate and replace by the resultant, F sub r. On the other side, purple, we have the force associated with this uniform pressure acting on this side. Okay, so you can either indicate as a uniform pressure, or since it's uniform, we know that pressure times the area, since pressure is constant, if we take this integral for the air pressure, pressure is constant, so it's just pulled out P times A, right? And it's a uniform pressure, so it just acts at the center of the area, or the centroid. So this would be F sub Pi, I could indicate, okay? And then that would just be the Pi times the total area of the hatch, which is just a rectangle L times W, right? But then we also have the weight, which will act downwards in the direction of gravity. So what color should we do it? So green, and through the center of mass. So we can write maybe W, which is our standard mass times gravitational acceleration. Okay, so those are the forces, and then we do have, we indicate that there's this point A that we're going to end up taking moments, right? So the resultant force times the point of application, okay? So this is the distributed force, the differential, and then the moment caused by the differential force integrated over the entire area would be the moment caused by the distributed force. And then if you would like to determine the point of application and then the resultant force, the point of application would be determined such that the moment caused by the resultant force is equal to the moment caused by the distributed force. Okay, so this y sub r would be this, y sub r. Okay, now, so as I mentioned, we can go through things step by step. So there's a diagram, the free body diagram of what's going on, okay? And the whole point of this is to determine this P sub I. Now, as I mentioned, if you're not sure what exactly to do, you can just follow step by step. So first, the orientation of the resultant force towards the surface, okay? Then the magnitude of the resultant force. So we can write F sub r is equal to the integral of P dA integrated over the area. Okay, there's a, well, let's see, what I'm seeing is that, okay, I call this point A and then area A, but we'll quickly replace A with the dy. So I will just leave it as is. You know the distinction. Okay, then the next step is pressure. So we have the expression for pressure, and so we can just substitute that in. So P naught plus rho GH dA. Okay, so the dA, so remember, here's the dA, okay? So this is the dA. Now, when I first discussed inclined surfaces, I indicated that it's convenient to choose a coordinate along the surface. Okay, so let me just go back to black. Okay, so let's define a coordinate y, where y goes along the surface. Okay, so this is y, okay, and then x could be into the board, and then there's like a corresponding z here. Okay, so x, y, z. Okay, now, if we want to integrate with respect to, or consider the y coordinate, okay, then the dA is going to be w dy. Okay, so the differential area is along the surface, so it's going to be a dy, and then into the board, the width is the given w. Okay, so then our differential area is w dy. So w dy. And y coordinate starts from point A and goes from there, y equals 0, and we just want to integrate across the surface to y equal L. So the limits would be from 0 to L. All right? Now, looks like a simple integration, except that we've got one more thing to take care of, and that's h, the depth. And we just need to express h in terms of y. So if we look at the diagram here, so here is our coordinate y, okay? And then here is our coordinate. Actually, let me do it in pink. So here is y, and then here's our coordinate h. Okay? So we just need to express h in terms of y. And y goes positive along the surface and positive downwards. But what we really need is the depth at each point with coordinate y, right? So because the surface is inclined at this angle theta, and what we really want is this vertical height. For any point y, we want the vertical component, okay? And then the total h is going to be d plus the vertical component of y, which is going to be, so that's going to be, it's going to be h. It's going to be basically h is equal to d plus, so this vertical is going to be y cos theta. Does that look right? Okay. So then you substitute that in here, and so we have the integral of 0 to L P naught, which is PA, so if you, well, let me just leave it as P naught for now, plus rho G times D plus Y cosine theta. And then that's this whole thing w dy. Okay? And then now, and again, theta is just a constant. Okay? It would be given, say, maybe 60 degrees or something. So these are all known quantities here. And so now, let me make that bracket. Okay, and then this guy here, this is PA, just a constant, given constant. So now it's very straightforward to integrate with respect to y, right? So if you do that, I mean, does anybody want me to work out the integral? It's straightforward, right? So then you get P sub A plus rho G D, those terms multiplied by L plus the rho G L squared over 2 cos theta, that whole thing multiplied by W. So you should get that for the resultant force. Then this point of application so that we can evaluate the moment. So then that's just, oops, we wrote that here. Here it is. That's just this. So in terms of y, that would be yf, f sub r, is equal to the integral of y df. Okay? And then our df is, the magnitude is pdA. So you can use right-hand rule when you ultimately sum moments about A. But for now, this will give us the magnitude of yf. So then it's really the same thing. We have df, which is pdA. So you just substitute that in, integral of y pdA. Okay, and then we already, we can make the same substitutions for pressure and dA as we did upstairs. And so we would just get then ultimately 0 to L. So this would be our P naught plus rho G D plus Y cos theta. And then we would have an extra Y term, D, W dy, right? But it's really basically a similar comparable integral, just one order extra of Y. And then so if you do this, then you would get PA plus rho GD, L squared over 2, plus rho G cos theta, L cubed over 3, and this whole thing, multiplied by W. Okay? Now, where is PI? So we have to evaluate PI here, and we do so by taking moments about point A. Okay, so we have YR times FR, or R cross F of the distributed force, is going to cause a moment in counterclockwise direction, right? And then the moment caused by FPI would be, so this is acting at the center. So an L over 2 would be its moment arm, and L over 2 times FPI, but in the, what did I say? This is clockwise. This is counterclockwise. So this L over 2 times FR, counterclockwise, okay? And then the R cross F associated with the weight, okay, we would need to take this component of W for that. So let me go back to the dark green. So the W, let me just rewrite it here. So here's our W, and this is the component of W that would cause a moment. The other component here would just go through point A, right? So we need, let me see, no, this is, here's W. This is the component that goes through point A. This is the component that causes a moment. This would be, if this is the angle, theta, so we would have, and this is W, W cos theta. Okay? And again, acting at, with a moment arm of L over 2. So this L over 2 times this component of the weight would cause a moment clockwise. No, counterclockwise, the same direction as our resultant force. Okay? So now let's see if we can do that. So we're going to, sorry, I'm trying to be color-coded, but it'll take me a little while. So now we sum moments about point A, okay? And we have everything set up. So we have, so right-hand rule is going to cause a positive YF, F sub R. Right-hand rule will be L over 2 times the W cos theta for the weight, the moment associated with the weight. And then the opposite sense, so we have a negative, and then again, an L over 2 is the moment arm for the force associated with the pressure. FPI, which we said was just pressure, uniform pressure, P sub I times the area, which is L times W, right? So this is just L times W. Now, this guy, and this is all equal to 0 to get our minimum P sub I, or that limiting P sub I value above which will cause the hatch to open. But you can see from this equation here that we have everything, and we can just simply solve for P sub I. But the one other thing to note here is that we didn't have to do really this step here, okay? And so if you originally looked and see what's going on, we could just immediately or right away sum moments. So alternatively, so this is method 2. By inspection, we could see we need to sum moments. And the sum of the moments would equal 0. And there is the moment associated with the distributed force, y df, okay, so plus, and then plus L over 2 W cos theta minus L over 2 P sub IA equals 0. And then you would do this as we did here. You could substitute in this expression and then basically do it all in one shot and evaluate P sub I from this equation. Okay? So that may save you some steps if you could see that that's how one could evaluate the P sub I. All right? There's a question back there? No? Any questions? Yeah?
The weight, is it W sine theta? If it's like that downward arm? For W cosine theta?
Yeah, this is, where's my pointer? So this W acts downwards due to gravity, and here's our coordinate system y. Okay, so there's a component in the y direction, and then there'd be a component, say, in this perpendicular direction. And the perpendicular component would be, let's see, yes, it is sine. Yeah. Yes. Yeah, I think I was going with the previous method. All right, so that makes sense. Good. Yeah?
In your equation for the magnitude of the resultant force, where does the L squared over 2 come from?
It comes from taking the integral of this guy.
You plug in L and y?
We integrate from 0 to L, so we're integrating with respect to y, and from 0 to L. Okay? Okay, so you can do the intermediate steps, but in the homework, I assigned 2 problems that involve force force on submerged surface. One is, the first one, I think 3.77, is a vertical surface. So the easier of the case. And then one is an incline. And if you understood this, you can easily do the other one. I mean, the assigned problem. Okay? And so I expect you to, on an exam, and actually on the homework, which I think I have, where's the homework? Right here. So for problems involving hydrostatic forces on submerged surfaces, these two, begin with vector equation, and then you show integration to determine resultant force and point of application. Okay? So as I discussed last time, not to use the equations in the text that involve looking up area centroid or the centroid location, but to just use, just as I did in this example problem, the basic equations. Does that make sense? Clear? Okay. All right, so what time is it? Okay, just enough time to maybe just go over. So let's start buoyancy. Okay, so let me see if I can just add a few blank slides. Okay, so buoyancy, to finish off chapter 2. So you know that if you have a submerged object or an object that's floating, then because of this pressure variation within the fluid, there would be some net force associated with it or acting on it. So let's consider, say we have some object, and here's the free surface of some fluid. So let's just take the example of an object submerged in a liquid, and we have our depth coordinate, h, and then at the free surface, we know the pressure P naught, and we know that there's a hydrostatic pressure variation as we go down in depth. So at the top surface of the object, you would have a lower pressure than the bottom. So there's a higher pressure at the bottom than the top. So if you integrate the pressure over the surface, there would be a net pressure force upwards, and that's the buoyancy. So let's consider then this net upward vertical force, that is buoyancy. So let me just write this down. So this net upward vertical force due to the fluid pressure is equal to buoyancy force. And we'll denote it as F sub B. Okay, so in order to evaluate, so let's consider some differential volume. Okay, and so if I blow it up, let's consider that it's a cylindrical element. And at this location, let's say this distance here is h1, and this distance, this distance here, the depth is h2. And we have this differential area, dA, and so this area here, dA. And so we consider the forces acting on this differential volume. So due to the pressure, we have acting towards the top surface, the local pressure. So let's call this P1, and then times the differential area dA. And then the bottom surface will have the local pressure P2 times dA, acting towards the surface, okay, in both cases. And so we have, now for the pressure, so if we assume rho is constant, okay, then we can use our usual expression, P is equal to P naught, where H equals 0, plus rho g H. So again, H is the depth coordinate, positive downwards. Okay, so here, let's look at then this net vertical force on our fluid element, our object. So this is the object. So this would be, so let's now define a coordinate z, positive upwards, okay? And then consider vertical force. So we'll have a dFz, the net vertical force on our object, cylindrical element. And so this is going to be, so positive upwards. So this is going to be a plus P2 dA minus P1 dA, that one acting downwards with respect to z. Then we have the evaluation of the pressure at each location. So P2, we can evaluate this in terms of H2. So this would be P naught plus rho g H2 times dA minus P1 would be P naught plus rho g H1 dA. Okay, and then, the P naughts cancel, and so we're just going to have our constant rho g, H2 minus H1 dA. So that's this differential force in the vertical due to the fluid pressure acting on the object. But that's the differential. Now we want to integrate over the entire object. So this would be, first of all, let's write this as this here, H2 minus H1 times dA. Well, this distance here is H2 minus H1, or the height of our cylindrical element, times differential area. This is a differential volume of our element. So to get the net vertical force associated with this pressure variation acting over the object, we just integrate dFz, which is the integral of rho g dV. Then, since we're assuming rho and g are constant, then this is just going to be rho gV. And this net vertical force we're referring to as the buoyancy force. And the rho, since the rho is the density of the fluid, then this is the indicated fluid. So this is the weight of the fluid displaced, right? So weight of the fluid displaced by the object. So that's the buoyancy force, the net vertical force acting on this object. And that's the well-known Archimedes principle. Okay, so very simple. You probably went over this already in high school, but of course it's, due to the hydrostatic pressure variation that we just went over. So, and of course we know it acts upwards. So as an example, let's see, do I have time for an example here? So the example that I have, since I just want to, in the last minute of class, just go over this example. An iceberg. So here it's partially submerged, right? An object that is partially submerged. And so we have this displaced volume, okay? And the whole entire weight of this iceberg is W. We also have the buoyancy force acting on the iceberg. It is submerged in seawater, which has density rho SW. The weight can be expressed in terms of the mass times mg, but it's the density of the ice. So if the iceberg is static, stationary, you just sum forces in the z direction. So positive buoyancy force minus the downwards weight. So you equate them. The weight is in terms of the density of the iceberg and the total volume of the iceberg. And then the buoyancy force is the density of the fluid, seawater, times just the submerged volume. And then here you can just solve for the ratio of the submerged volume to the total volume is equal to the ratio of the density of the ice to the seawater, which is 0.9. Or you can evaluate 1 minus this, which would be the ratio of the volume of just the tip coming out to the total volume, and that's 0.1 or only 10%, which is why people are always saying tip of the iceberg. So that's the example problem there. Okay, next time I'll finish off, Wednesday, finish off chapter 2 by going over the case of rigid body motion, where we can use the general equation that we developed initially with an acceleration term, and then we'll move on to fluid dynamics, chapter 3. Okay?